Good day, and welcome to our webinar on the how and why of plant energy management. Things you can do span from the simple to the strategic. Brought to you by CFE Media and Technology. Joining us today will be Mike Stowe, a senior energy engineer with Advanced Energy in Raleigh, North Carolina. I'm Kevin Parker, editor of Plant Engineering Magazine. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. To take the Learning Unit exam, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. Today's presentation focuses on the value of strategic energy management, whether that means something as simple as tracking energy costs or complete solutions such as benefiting from energy management certification programs. This webinar will help attendees understand where their facility fits along the strategic energy management continuum and what the costs and benefits are for its various levels. A particular focus will be on the use and implementation of the DOE 5001 Ready Navigator tool. Here are some tips to help you get the most from today's webcast. If you experience issues with your slides or audio, refresh the browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of this webcast by adjusting the volume on your computer or on the webcast platform. For technical problems with audio or slide presentation, click on the question mark at the top right-hand corner of the screen to access system checks to try before contacting an online technician. If a technician is needed, type a message in the Ask a Question box and someone will get to you as quickly as possible. The Ask a Question box is also used to ask questions of our speakers. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded. You will receive an email within a week with the link to the on-demand event. To download the certificate of completion, PDF copy of the presentation, and additional resources, use the Event Resources tab on the left-hand side of the screen. Those documents will also be available with the on-demand version of this webcast. I'd now like to introduce today's speaker, Michael Stowe, a senior energy engineer with Advanced Energy in Raleigh, North Carolina. Mike has more than 30 years of experience in manufacturing plants, including roles as production manager, maintenance manager, and plant engineer. Mike has extensive experience with industrial processes and plant facility systems. Today, Mike works with utilities and industrial equipment suppliers and manufacturing plant teams to identify technologies for energy-efficient solutions. Mike has developed and delivered presentations on industrial energy efficiency and related topics for utilities, industrial trade associations, and technical groups. Finally, Mike has a mechanical engineering degree from Georgia Tech and has trained as a submarine officer at the U.S. Navy Nuclear Power School. Michael, welcome to today's webinar, and please go ahead.
Thank you so much, Kevin, and it's a real pleasure. In those years when I did work in the plants, one of my favorite magazines was Plant Engineering Magazine, and I still get it, even though I'm doing more energy work. I love it, and it's a real pleasure to get to speak with you all today. So thank you very much for that introduction. And just a little, our agenda today, we're going to go through a little background information. I want to talk about why strategic energy management is important and some of the things that it is good. Why would you do it? And there's something we call two key pie charts we'll talk about. We'll talk about some ways to save energy in the manufacturing plant. Some of these will probably be very familiar to you. We'll talk about your energy team and what you really want to have there, and why 50001 Ready. 50001 Ready is a tool developed based on ISO 50001, an energy standard, and we'll talk about that some. The commitment, 50001 Navigator tool itself, and some of the outcomes. And then, of course, we'll have a time for review and questions. So my background is basically making stuff. These are things we've made. And the point is just that I've worked over the years making various products, but just think about this in terms of it takes energy to make stuff. You've got to bend this metal, you've got to melt metal and machine metal and melt plastic and bake cookies and make bricks, whatever you're maybe making in your manufacturing or plant, it takes energy to do that. And where does that energy go as part of your process is an important part of managing that energy, is understanding where it goes during the processes. So these are products from places I've worked, primarily automotive related industries. And here's just another example. Think about an excavator, a big backhoe, a big tracked backhoe you might see by the side of the road. And just think in the back of your mind, all the processes, all the energy that it takes to build something like this, hoses and electrical wires and big metal castings and weldments and all kinds of things that go into building something like this is a complicated example, but just and understanding that process is very important. Why strategic energy management? Where does all my energy go? We're going to talk about that and why that can be very important to helping you manage your energy. This is a graph that was initially developed by DOE, Department of Energy, and we've used this also and developed it a little more, but we call this the strategic energy management continuum. And if you will, the bottom is the base. There's lots and lots of people that do basic energy management, and it's relatively simple. And there's fewer and fewer people that do very complex energy management. And there is a program called Superior Energy Management sponsored by DOE, which is like the ultimate. I kind of relate this to high school, bachelor's degree, master's, and PhD in energy, if you will. So what the key of this is to try to understand where are you along this continuum? Are you just wanting to start putting your power bill in a spreadsheet, or are you already doing some of these programs and want to get even better? But the key thing is to figure out wherever you are and start there and improve from there. And there's no, you don't have to start at the top. You can start with the basics, and then you can move up this continuum and do more and more energy management. You can get, there's a Better Buildings plant. Some of you may be in the Better Buildings plant with Department of Energy. There's the 50,001 Ready program, which uses the 50,001 tools. There's certification in ISO 50001. And of course, there's SEP, which 50,001 certification is a prerequisite for superior energy performance. So anywhere along this scale that you are or want to start, that's great. Know where you are, start from there, and that's great. That's wonderful. There's lots of tools, lots of systems and things out there to help you. Just a little bit about energy, or why do we need to manage energy? Well, there's a lot of it out there that we're consuming in the manufacturing area, and commercial buildings is huge. This is a spaghetti chart, and you don't need to memorize this, but on the left-hand side are all the energy sources. These are all the dead dinosaurs: oil, gas, natural gas, petroleum, gasoline. You can see how huge this big green bar is for gasoline. And this tiny little yellow bar over here is electric vehicles. So we talk a lot about electric vehicles, but in reality, they're not making a huge impact, but you can see the potential there. But anyway, right here, these two boxes here are the commercial and industrial energy. And you can see industrial uses a lot of natural gas, a lot of oil, a little bit of coal, and a good bit of electricity. But a lot of energy goes to making electricity. So you've got a lot of coal, natural gas, hydro, nuclear, solar, creating electricity, and then the electricity is spread out to other people. So in the big picture, it's split about a third, and a third between transportation, which includes airplanes, cars, boats, everything. Commercial and residential is about a third, and industrial, where most of us operate, is about a third of the energy consumption. If you break down this industrial piece, this is what it's really made up of. Lots of natural gas, lots of petroleum, a little bit of coal still, which is unusual. But I've worked with plants here in North Carolina that still have coal-fired boilers still in operation today. Biomass, and of course, electricity. So mapping out the energy, looking at those previous charts to quantify that, there's 35 plus quadrillion BTUs used for commercial and industrial energy. That's combined electricity and fossil fuels. But just to put that in perspective, a quadrillion is a number with 15 zeros after it. So the bill that just passed the Senate and House, that was around $2 trillion. Well, this is another whole set of zeros past a trillion. So you got million, billion, trillion, quadrillion. So it's a lot of BTUs, a lot of energy out there. A lot of it needs to be managed, and managing it and make your plant more efficient and save you some money. And basically, the basic thing we look at is we want to make more with less. If we're making bricks, we want to make more bricks per MMBTU. If we're baking cookies, we want to make more cookies per kilowatt hour. Similar to lean principles, we want to eliminate the waste. And there's a lot of waste out there to look for. And one of the ways to do that is to focus on an energy intensity for your plant. If you're doing something by the ton, how much energy are you using per ton of production? Whether it could be cabbage, it could be peaches, it could be bricks, or maybe you're measuring something in a length. You're making lengths of stuff, like maybe cloth or something by yard. Or maybe you're making widgets, maybe you're making gears. So you want to do, how many MMBTUs am I doing per widget that I'm making? And understanding this energy intensity can really be a data point for your energy management. Transformation is, what are my raw materials and what do I end up with shipping out the dock? My raw materials are flour, oil, and chocolate chips. My product is chocolate chip cookies. But what do I have to do in between the raw materials at the shipping dock or at the receiving dock and the final products at the shipping dock? And mapping out that energy and understanding where it goes is important. So, for example, at a foundry, you've got this big giant pile of scrap metal, and you end up with a nice, beautiful cast iron Y sewer fitting. Something has to happen between this point to get to that point, and mapping that energy out and understanding the energy that takes to get there. Again, making stuff takes energy is important. Here's another example. This is actually from one of the plants that I have worked at. You take a round bar, a long 20-foot piece of round bar, and you end up making a very detailed finished front-wheel drive half-shaft outer race bearing. This probably has 37 steps to get from here to here as a finished product. Very complicated, lots of energy points, lots of heat goes in here, lots of machining. But what does it take to make this? What does it really take to transform this steel bar into this finished product that you can sell? And all the way along, when you add energy, you also want to be adding value. Thus, still the tie back to lean manufacturing. Here's a little diagram. I love this little diagram. We use it all the time. Again, make more with less. Energy efficiency. How much energy am I actually getting into my product to add value to my product, to make it more valuable so I can sell it based on all the energy I pay for? Well, you pay for the energy. Your natural gas meter turns, your electric meter spins, it comes into your plant. Where it goes from there is somewhat up to your processes. And what you really want to do is eliminate this line. Now, you'll never get to zero. Physics and thermodynamics will not allow this loss to be zero, but you can certainly minimize it. And, combustion processes, a lot of that heat goes right up the stack. You got compressed air that just leaks out everywhere. The compressed air doesn't go add value. It goes out into your building. So these are losses. So you want to minimize the losses and improve how much energy goes into adding value to your product, because you've already paid for it. You've bought the energy. So once you've bought it, you own it. And you want to manage this part of it so these losses are minimized. So again, energy intensity, we had some examples, but just think about, you want more tons of metal melted and cast in a foundry. You want to produce more gallons of formaldehyde in your chemical plant. You want to produce more gears per kilowatt hour at your gear factory. So energy intensity is a unit of product per unit of energy. And there's a relationship between the two. Remember, all this baking stuff takes energy. This picture here is induction hardening of gear teeth. Almost every part that touches another part that's metal, like gear teeth or splines or things like that, are induction hardened because they make excellent wear surfaces. And that takes a tremendous amount of energy to turn this gear red hot, and induction harden it. But this is the relationship. You want to increase energy efficiency. You want to make those losses on that little diagram minimum, so you have the most energy efficiency in your process. And by doing that, you'll in turn reduce your energy intensity. So if you improve, say you have a process that's 80% efficient and you improve it to 90% efficient, well, now your energy, the numerator of that number or the denominator, is going to go down. So your parts per kilowatt, or if you turn it up down, kilowatts per part, your energy intensity is going to improve. These are related. And one of the ways that we do this is to map out the process. This is a very busy slide, but it just gives you an example of how you can connect the dots. The blue boxes are processes. The blue arrows connect the processes. Orange boxes are energy loads. Yellow boxes are the actual energy source, like natural gas, fuel oil, whatever it may be. But this is a very good exercise, and a lot of plants already have this. They just haven't really looked at what energy goes into what box, but a lot of plants outline the processes. Actually adds the energy, so you know, what are the energy sources? What are the significant energy users on here? What's really spinning the meter? Is it a combustion process? Is it, you know, think about a foundry, their thing that whatever melts the steel is going to be a big user. But what are your big significant energy users? And you want to focus on those first. So that's a very valuable process that you can use. These are the two key pie charts that I talked about. One's very relatively easy and one's more difficult, but you really want to be able to do an energy review. 2001 Ready system helps you do this, but you want to know what comes into my plant. And this is usually natural gas, electricity, and maybe some LP or diesel or fuel oil in some small amounts. And then where does it go? You know, where does it go in my plant? Is it motors? Is it chillers? Is it air compressors? Is it a process? Is it a paint oven? Is it lighting? Is it data centers? You know, breaking that down and understanding where that goes. And that can be complicated. You know, if you don't have lots of sub-metering or stuff like that, it'd be hard to do. But understanding these two, the strategic energy management process really gives you a leg up on this. Non-energy benefits. One of the benefits of doing strategic energy management, if you do energy projects, sometimes you'll get a non-energy benefit, improving in safety, reduction in emissions, an environmental plus. You may have some labor savings or reduce scrap. So sometimes when you do an energy project that can, you know, improve an energy or improve a process, you can also get some non-energy benefits, and those can be very, they can also have cost savings related to them. So let's talk about some ways to save energy in the manufacturing plant. And most of these are applicable to any manufacturing plant. But I typically break this down into two parts. When you have a manufacturing plant, basically you bring in raw materials, you process them, and you make a product. Those processes are one area to look for energy savings. The other area is every plant I've ever been in always has facility that supports the processes. You've got air compressors, chillers, boilers, ventilation, air handlers, cooling towers, all types of facility things that aren't making the product, but they're supporting all these processes to do. So you kind of split this up in these two areas to really focus on looking for those energy savings. So looking at the process, again, think about this little diagram. You know, you got this round bar and you've got to make this final beautiful part. And you want to kind of focus on the transformation. When you're looking at your processes, you really want to look at what energy is consumed to get the product from the receiving dock to the shipping dock. You may bring in 27 ingredients or round steel bar or all kinds of different stuff you buy and bring into your receiving dock. And then you start manipulating it, burning it, cooking it, cutting it, whatever, mixing it. And if you finally get something that you ship to your customers or ship to another process, you may be an intermediate building a product that somebody else puts in their product. But what does it take to transform that from the receiving dock to the shipping dock? And that's a good process to think about. Again, going back to the block diagram, it's very useful to map that out. let's talk about a specific process that almost every manufacturing plant has in some form is combustion. Most people have boilers or some kind of ovens that are heated with natural gas, and that's a process. It could be curing a coating on cloth. It could be baking cookies. It could be curing bricks. It could be drying grain. It could be doing any number of things. But the basic process is the same, and there's ways to think about it in terms of a process. Methane plus oxygen gives you carbon dioxide and water. That's combustion all day long, everywhere, anywhere you go. This could be oak firewood plus oxygen gives you carbon dioxide and water. It's the same everywhere with fossil fuels. And again, as everyone realizes, and most people are concerned about, this carbon dioxide is bad. You want to minimize this. You hear people all the time, we want to minimize our carbon footprint. Well, if you're burning natural gas, you got a carbon footprint. So that's the equation. This is just a graph. It's been around forever, but it's just like, I don't know if anybody plays with their carburetor on their car engine, but you want to show and optimize it. There's certain amount of excess air that makes you run more efficient. This top curve is efficiency. So if you can be in this sweet spot, you're going to run your combustion process as best as possible. If you don't have enough air and too much fuel, you're going to fall off way over here. If you got too much air, you're going to fall off over there. So if you have a combustion process, one of the things you can look at is your excess air and optimize that and put controls in place to maintain that. Other things you can do is waste. Combustion is one of the biggest wasters. We probably put out enough heat from our manufacturing plants here in North Carolina to heat all the houses in North Carolina. It just, so much of combustion goes straight up the flue and heats the neighborhood and doesn't do anything to add value to your product. And you see this all the time in combustion processes. You're heating up the walls of the furnace, you're heating up the conveyor belt, you're leaking out but most of it goes straight up the chimney. But some of it does get into your product and make it hot and adds value and does what it does. But looking at a process, you want to understand those losses. Lean manufacturing, eliminating waste, and that's a big one. That's an opportunity in almost every plant that I visit. Waste heat recovery, by the same token, this heat going up the chimney, can we use it? Absolutely. Having a recuperator, having a method to preheated combustion air will make huge improvements. Just decreasing this stack temperature by transferring about 40 degrees into this combustion air can increase the efficiency 1%. Take advantage of that if you can, especially if you're making new purchases. It may be hard to retrofit an old boiler, but if you're buying a new boiler, make sure you got some kind of recuperator on that thing. So let's look at facilities. Let's focus on facilities. That was kind of an example of a process. And there's lots of others. If you're baking cookies, track your dough from the receiving dock to the shipping dock, including all the packaging and everything else, and figure out where those energies are. But you can do a good analysis on processes. That's one source of energy savings. Another good source is your facilities. And some of the biggest users are motors. Most manufacturing plants, between 50 and even up to 70% of their electric load is motors. Motors turning any number of things, conveyors, cutting machines, chillers, compressed air, and HVAC are all big users of motors. Even boilers, you can't even do combustion without motors because you got to have combustion air moving. If you're making hot water, you got to pump the water. So there's always some electricity associated with combustion processes, but motors is huge. And there's lots of ways to save with motors. But motors typically account for, like I said, 50 to 60% of a manufacturing plant's electrical use. And we recommend and implement a lot of times a motor management program. And what the motor management program is you really document all your motors. And that can be a daunting task initially, but once you get it done, you've got it. You may have 500 motors in your plant. Now, you don't need to go get every quarter horsepower motor, but maybe pick a cutoff. 10 horsepower and above, we're going to document. We're going to take a picture of the label plate. We're going to put them in an Excel spreadsheet. And what you want to do is over time, you want to maximize the replacement and purchase to maximize the efficiency of these motors by consciously tracking your motors and watching them. So that can be a very lucrative way. And you always want to buy NEMA premium motors, always. I'm not even sure if you can't buy them now, but it's probably the only thing you can buy. But another thing is to use variable frequency drives with your motors. And the reason they can be so dramatic in savings with a VFD is the ratio, the laws of horsepower versus the speed is a cubed. And just to show an example of this, a ratio of cubes. So if you take a half, you take speed from 1 to 0.5, and you cube 0.5, you get roughly 1/8. So if you just reduce the speed of a motor by half, you reduce the power to 13%. That's huge. That's huge. One thing we see with VFDs though is a lot of people think they're magic, and that we should put a VFD on everything because they're magic and they make us save energy. Well, actually, if you just put a VFD on something that has constant load, it actually takes more energy because now you got to power the frequency drive as well. You have to have a V. You have to have something variable for a variable frequency drive to make sense. Okay, if you just put it on something that runs at constant load, you're not going to save any energy. But if you have a fan that supplies air, and depending on the outside air temperature, it can run slower or faster, or if it's a hot day, it has to run at 100%. It's just got to pump cool air. But on a October or April day, maybe it only needs to run at half speed. You don't need to move all that air. If you put a variable frequency drive with an outside air temperature feedback on it, i.e. variable, then you can get some real savings. Nameplate data is very important. For your management motor program, hire a co-op for the summer and have him go do your entire plan and take pictures of nameplates on motors and build a database for you. It's a great, great tool to have. Another thing about motors, spend the extra $100 to buy the premium efficiency motor. And here's why. Over the course of a 10-year, say it's a 10-year life of a motor, about 4% of that cost is the initial cost of the motor and maintaining it. The other 96% of the cost is what the electricity takes to make it. So if you buy a motor, even if it's only 0.5% or 0.75% more efficient, over 10 years, you're going to save tons of energy. And you'll pay for that extra premium efficient motor cost in a couple months, but definitely in a year or two. So life cycle costs can be very important, especially with motors. You don't want to run motors at a very reduced load because efficiency drops off significantly. If you want to right size motors for the load they are. So you want to run them up here where they're most efficient. But as you can see, as the load goes down, if you run a 100 horsepower motor at maybe 50 horsepower load or even a third load, it just starts dropping like a rock. And the smaller the motor, the worse it is. So right size your motors. Compressed air, we could do a whole week's seminar on compressed air for sure. It is one of the most expensive, least efficient things. And if we could build stuff without having to use compressed air, it would be great. But the good thing is you can usually get excellent payback on projects because it is so expensive. But just to put it in perspective, a 150 horsepower compressor, which is not that big, running a full year with a nickel per kilowatt hour as the electrical cost is about 50 grand a year just to make that compressed air. And then if you leak some of it out, now you've spent $50,000, but you've only delivered $30,000 worth to the process. A lot of plants, there's an attitude that air is free. I've seen air used for personal cooling and all other types of things where it's just blowing out, use it for a blow off. Oh, I got compressed air. Where's my hose? Let me just blow this off. And it's just not free. It's extremely expensive. Typically, we see air leaks, and we do lots of measuring, 25 to 30% of a capacity. So if you have 200 horsepower air compressors, that's 400 horsepower. Well, maybe 100 to 150 horsepower of that's doing nothing but supplying leaks. It's terrible. A 1/8 inch diameter air leak or hole in a pipe on a 100 PSI system costs about $1,000 a year to generate that, compress that air and then have it leak out. 1/8 inch diameter. That's pretty tiny. So say you've got 60 of those in your plant, 60 equivalent 1/8 inch diameter leaks. That's $1,000, $60,000 going out the door or out into the atmosphere. These little nozzles, that you can buy these little nozzles for about, I don't know, 20 or $30, and they're energy efficiency air nozzles. If you have a lot of blow-offs you need to do, these are great. They make use of the air, but they also entrain other air, and they're very efficient and help. Also manage your system pressure. We found plants that were running at 125 psi because they had one machine that needed 120 psi, and the rest of the plant could run on 90. If you could get a little compressor just for that 125 machine and then put the rest of the plant at 90, you can roughly save 1% of energy for every 2 psi you drop. So if you drop from 120 to 90, that's 30. You could save 15% of your compressor energy right there. Air leaks. If you have an oil leak on the floor or water leak, people see a puddle, people step in it, people slip, and you mop it up. But air leaks they don't leave a puddle. You don't see them, and sometimes you don't even hear them if they're small. So they kind of get forgotten. But an air leak program and an air repair program is cheap, no cost, no capital, and it can save a ton of money. Talk a little bit about chillers and HVAC. Chill water setback temperature is basically all that means is you take advantage of your cooling tower and run the chill water as cool as you can back to the chiller. But you don't want to go below about 65 degrees to your chiller. But if you can run it cooler, it's much more economical to run the fan on the cooling tower than it is to have the compressor on the chiller run. It's usually probably a 10 times or 20 times as big of a motor. So set condenser water reset, setting back the chill water temperature. If you have daily cycles where you don't need to have as cold of water, or if processes can bear a 45 degree instead of a 44 degree, that can work. VFDs, again, we talked about VFDs on chilled water pumps, cooling tower fans. All these can be very, very good. Ice storage systems, if you can run off peak at night to make ice and then use that ice storage the next day for cooling, all great stuff. Lighting, not too much to say here. LEDs are the latest and greatest. There's lots of incentives typically from utilities, and there's lots of vendors out there that are set up to help you do a lighting project, and typically the savings are huge and the paybacks are decent, especially if you get local incentives. Maintenance practices, just doing good general best practice of maintenance can save energy. If you think about a motor on a fan pushing a fixed amount of air through a filter, if that system needs 1,000 cubic feet per minute, it takes more amps to push that air through a dirty filter than it does to push 1,000 cubic feet through a clean filter. So other things, vibration, misalignment, looking at thermography, insulation. You can have a lot of cost associated with chiller and steam piping not being insulated, because that heat is just going out the atmosphere, or that coolness is going out the atmosphere. It's not insulated, and the chiller has to make it up. Steam traps are notorious losses. Compressed air leak repair, cleaning, and we'll look at a couple of these. Cleaning is great for good energy heat transfer. Ultrasonic air gun should be in every maintenance toolkit. Ultrasonic can look at piping in the ceiling. It can listen to piping. It can listen to vibrations. It can listen to bearings. And it's got an ultrasonic. It can do vibration analysis. It's a great tool. And you can literally hear air leaks that you can't hear with your just a human ear. Fixed forward-looking infrared radiometers, or just IR infrared cameras, are great. They're good for electrical. They're good for looking at bearings and motors and seeing what's hot. This is an example. This isn't the same picture, but if you can imagine your insulation on your steam pipe looks something like this picture, and then you looked at it, you're going to see a lot of where the purple is where the insulation's in place, and where this is glowing yellow hot on a temperature scale over here. The insulation, you're just radiating heat to atmosphere. You can also use it for building envelope test. We used to do this all the time. We thermography our entire plant main breaker panels once a year. And what you see here is there's an air gap developed on this contactor, and an air gap makes it harder to push the electricity through, so it arcs, and it reduces the efficiency of the energy transfer. And since the energy has to be conserved, it turns it into heat. So these two might be at, say, 100 degrees, and this one's at 180 degrees. It's because it's loose. So what you do is you turn the power off, you go in, you tighten up these lugs, check things out, put it back together, take another picture, and they all look good. So that's a very good process. Cleaning, I'm sure you've never seen anything like this in your plant, but if you did come across it, tube sheets, refrigeration coils or condenser coils on HVAC heat pumps and so forth, dirty filters, all this costs energy. It reduces energy transfer efficiency. It takes more energy to run your equipment when it's in this kind of condition. So cleaning is good. Talk a little bit about, so there's just some tips and ideas about how some things you can look at your plant to manage your energy and save some of your energy that you're trying to manage. And just talk a little bit about the energy team. Cross-functional teams tend to be very good, and we've seen very good success with having people from purchasing and even finance, human resources to help you with your communications. Certainly operators, people that are operating the equipment, and the facility guys that are operating sometimes the biggest users like the chillers and the air compressors. Contractors, a lot of people outsource their maintenance nowadays and have an HVAC contractor. Your local utility account manager, a lot of times they have incentive programs or other types of programs, but involve all these people on your energy team. And the energy teams we see kind of have three levels. There's a core team. There's like what I would call peripheral team members that tend to, come and go. They come for a while, help you with a project, and then they go away, but they're not on your team all the time. And then you got your site leadership. And basically, the way to think about this is the core energy team basically is the most time commitment, and they're focused on energy management. And then you have the what we call like a concentrated time commitment. Say you're going to roll out a program or do something, so you need like IT guys or some operations people because you're doing a paint booth project or something like that. So you have a couple operators on the team for a couple months. And then, of course, your site leadership. You want to involve your plant manager, your site leader, your corporate. Maybe you have a corporate energy management team or something, but there's some leadership people that you want to involve from time to time for sure. And then if you're a corporate office with say you're a corporate office and have 7 sites across 2 or 3 states, how does the corporate office fit into the team? Do they help lead the efforts and kind of combine efforts across the 7 sites? And you see that scenario quite often. So why 50001 Ready? How can 50001 Ready help you attack this need to manage energy? It's a great tool. It was developed. It's based on the 50001 standard. There's an ISO 50001 standard. If you have ISO 14000 for environment, or I know a lot of you have ISO 9000 for quality, many of those principles are identical. Very, very similar principles based on the Plan, Do, Check, Act. You plan your work, you do what you said you were going to do, you check to see if you did it, and then if you didn't do it, you act to fix it. Plan, do, check, act is common across all ISO, and ISO 50001 is no different. But 50001 Ready is based on the standard, and it really provides a system that you can use, the Plan, Do, Check, Act system that you can use to implement energy management. It uses 25 tasks. And there is in a online system that you can log into. It's all completely free, and it's like this is the login page. There's 50001 Ready. You can set up an account, put your email, set in a password, and you can set you up an account right there. And this is it's measurable. It's data driven, and basically you set up performance indicators or things you want to measure, and you set targets and you measure it and you compare it to the baseline, and it's very what I call user friendly in the terminology and language that it uses in 50001 Ready versus the you shall do this language of a standard. It's very practical and very useful. There's proven results. The Schneider Electric and the 3M company, that 3M makes Post-it notes and a lot of other things, but they showed a big difference in plants, their plants within their own plants. People that used 50001 had almost double the average energy savings versus plants that didn't. Now, the plants that didn't still had energy savings, and that's wonderful. But 50001 will help you be more formal and more intentional, and you will get better results. And that's at least proven with 2 different companies. So that's what you want, is continual improvement of your energy management. ISO 50000 is comparable, and we mentioned this, you should leverage other ISO systems. If you have other ISO systems, you should leverage those and use those. It's not a requirement. You can absolutely start 50001 from scratch and build from there using 50001 ready. If you have some of these other systems, you should certainly leverage those because there are certain systems that would overlap. In summary, 50001 Ready, the tool is free. It's an alternative to getting full certification. It's performance and data driven. You make decisions based on facts, not opinion or anything else. It's a step-by-step process. There's proven results. You have dashboard tracking, lots of great resources. So let's talk a little bit about specifically the 50001 tool. You log in, you have a dashboard, you can set this dashboard up, you can click here and build your team, you can assign teams, you can assign people to be a user or an administrator. You can set up a multi-site. This is an example of a corporate with 4 sites. If you have a corporate headquarters and 20 sites, you could set them all up in here. And this is a little dashboard. It's a little hard to see, but those are 25 gray boxes. And as you complete the task, you can mark them in progress or in review or completed. And gradually you'll grow across and finish them all for all your sites. But it's a great dashboard. Every task has its own tab that you can use. Here's the 25 tasks. I'm not going to read these, but they basically go from plan, do, check, act across the top. You plan your work. You have a management policy or an energy policy. You do some energy review. You pick your big users and things like that. You have training and awareness. You have operational controls, and it's really, really practical. And these 25 tasks, each task has a playbook. And you can download this playbook, and basically it's a script or a guide, fill in the blank, checklist to guide you through the requirements of each task. And you could literally take these 25 playbooks, download them, do some due diligence and homework, and set up some things with these 25 playbooks and have you a superb, excellent energy management system. It really works. And it's all download. You don't upload anything to 50001. You don't put any of your data, you don't put any of your playbooks back up. It's strictly a download. It's a great system. It also offers some footprint tools, which you can put in, like I have electricity and natural gas and other things in here where you can track your energy. A lot of you probably already do that, but that is available and is free. And it has an energy measurement tool if you want to measure your energy performance over time. Like you could have a baseline of 2015 and you want to see how you've improved from 2015 to 2020. You can dump some data in here and it'll automatically calculate that for you. There's just some sources. I wanted you to have these in the recording. So there's some sources for all the stuff we just talked about. Some really good stuff. Just to go in the 50001 Ready and learn about it. If you want to just sign up for a Navigator account, you can just click on navigatorlbl.gov. But you'll have this and you can see it. You can play with it too without setting up an account. You can look at some stuff. Here's the footprint tool and the light tool. And then Better Buildings program also has a lot about 50001 Ready. So what's the point? You know, we want to manage our energy. 50001 Ready is a great pathway to do that. What are some of the outcomes that we can expect or look at? One of the things is you will definitely gain an understanding of the 50001 standard by using 50001 Ready. It's based on the standard. It covers most every aspect of the standard. It kind of divides it out over 25 working tasks that you can work through. You have the playbooks available to help you get there. Use the 50001 Ready Navigator. You know, that's one of the desired outcomes. Use the Navigator. Download those 25 playbooks. Read the tabs and understand what the intent of this. This helps you understand the intent of the standard. Sometimes the standard will say, "You shall do this," and you're like, "What does that mean? I mean, what does that mean? What do I really have to do?" This helps you understand what you really need to put in place or review or think about or look at or consider or train people on to really complete what the shall means. It's a kind of an interpreter's guide to the standard. It's very, very useful. You can gain recognition. There's a program for 50001 Ready recognition. This is not a third-party audit like certification. for 14 or 50,001. This is something where you say, I've done the 25 task playbooks. I sign off that I've done it. You mail it in to DOE and you send them some energy performance where you said, I measured my energy performance. And this is where I am, and they'll recognize you. It is a certificate, but you're not certified in the sense of ISO, like ISO certification, but you do get a certificate for participating, and you get recognized as being, have completed 50,001 ready. And that some people, that's really what they want to do. And it's self-attesting. Nobody's looking over your shoulder. Nobody's going to come do a third-party audit. You say you did it, and it's an honor system. And it's a lot of people do it. A lot of people do it. Energy performance improvement. This is the whole point. That's the desired outcome. We want to make more bricks per kilowatt hour. We want to bake more cookies per MMBTU. So energy performance improvement is the whole, that's why it's in red. It's very, very important. And then, of course, a lot of times when you manage your energy so well and do energy intentionally targeted, prioritized energy improvement projects, a lot of times you actually improve your overall plant operations. So that's a real benefit. So how do you get started? Let's think here, and here's some of the many resources available. Your local utilities, your gas company, your electrical utility. Typically, electrical utilities, in my experience, have account managers for large accounts. If you're a big manufacturing plant, you may have a specific account manager from the electrical utility. Use them, engage them, tell them you're interested in 50,001. Do they have any incentives, or do they help pay, for you to get some help to do 50,001, or are there programs available? The DOE programs we've talked about, the 50,001 Ready Navigator, you literally could go log on to it by yourself, get the playbooks, work through it, and develop it. There's Better Plants program. There's also Superior Energy Performance. But there's programs out there that are available and free resources. If you do need help, maybe you do need an energy consultant, or you want somebody to help you walk down this 50,001 path. Certainly there's tons of energy consultants and also some government subsidized programs to help you get a consultant. There's the DOE resources, all the training materials for 50,001 Ready. There's cohorts. Cohorts is like a group of 5 to 7 companies that get together. Maybe you get 5 to 7 companies together, and they're all going to go through the 50,001 Ready playbook together. They're going to go through the process together. It might be 6 months, and you have 7 or 8 training sessions. You have one-on-one calls. You work with the plants on their energy review and the playbooks. And there's lots of cohorts, and there's some funding available for cohorts through the DOE. And then, of course, if you do want to get certified at some point, moving up that pyramid, there's the verification body, and there's lots of them out there. If you want to get certified in ISO 50001, you would need a verification body to come do a third-party audit as a partner. And these can be very expensive. I mean, it can be up to $30,000 to get an audit for 50,001 certification. That's just a rough ballpark number. Imagine your company right here. You have lots of help if you want to get started on energy management, be it just 50,001 Ready, just some basics, a Better Plants program, talking to your utility, talking to an energy consultant. There's lots of help available to get started down this road. 4 out of 5 energy consultants survey recommend 50,001 Ready to prevent this from happening to your energy team. Now, I do have a little disclaimer down here that says no actual survey was taken. This is just to make a point. But we believe, we've seen it, we've used it, we've watched companies use it, and 50,001 Ready is a great tool to help you implement 50,001. Even if you were going to get certified, for sure, 50,001 is a great way, 50,001 Ready is a great way to prepare for getting certified. If you don't want to get certified, but you just want some recognition, 50,001 Ready is a great program. If you just want to get started and learn a little bit about energy management and maybe do a few of these things, take a look at 50,001 Ready and maybe start with a couple tasks and do a couple things, and then you can grow from there. Just remember to start where you are and improve from there over time. That's what it's all about, continual improvement. So just quickly to review, we talked about these two key pie charts. What do I pay for? And then where does it all go in my plant? We talked about some ways to save energy. Don't let these pipes heat up the building, keep the heat and the steam. We talked about this pyramid and where, figure out where you are and go from there. We talked about the 50,001 ready tool and so forth. So covered a lot of stuff, and I think we're about good time for some questions.
Well, thanks, Michael, so much. Really appreciate it. A lot of presentations purport to be practical, but yours was really down to earth and had some great stuff in it. So we got a lot of questions. Let's start getting to them right away. I got a little message here. Let me see what that says. All right, we got 10 minutes left. First question, what are some good, easy to use tools for energy analysis?
Yeah, that's a great question. And, my go-to energy analysis tool right off the bat is an Excel spreadsheet. And I'm not being silly, there are plenty of tools you can download, but just to get started, to really kind of see where you are, to be able to build that one of those pie charts, you really want to have your data in an organized place. So if you have months down one column and kilowatt hours down the other, or MMBTU for natural gas or whatever, and then you combine it all together and make your pie chart, that's it. Now, looking at some of the links back a few slides, the DOE has many tools. They have things they call like Pump Master. They have the Compressed Air Challenge, which is all about compressed air. They have pumping tools where you can look at pumping systems and optimize those. The internet's full of that kind of stuff. And, but basically you can go on the internet and look for tools. 50,001 Ready has lots. If you want just a basic energy analysis to figure out where your energy is and then where it's going, there's other things. Figuring out where it goes is a little more complicated, but a good old Excel spreadsheet can really be good.
Next question. How does energy efficiency measures in a plant operation compare to those that would take place in a commercial or institutional building?
Yeah, the one thing typically for industrial plants, their energy efficiency can be all over the place because it depends on what they're making. Typically in a commercial building or a hospital or a college campus or something, those buildings are primarily heating and cooling and lighting, the things that you have to do for people to be comfortable in an occupied building. So, for example, in a commercial building, you're not going to be mixing and heating up peanuts to make peanut butter, but you do have lighting and heating, and those, are pretty relatively simple to determine. Hey, if I've got a boiler that's this efficient and a HVAC or chiller that's this efficient, I can figure out pretty quickly what a good benchmark. And there are lots of good benchmark data out there. What is a good benchmark for my commercial building? Is it 27 kW per square foot, or is it 50 kW per square foot? And where am I on that scale? There's also benchmark tools also with DOE for different plant operations in different segments of the market. So if you're a foundry, or if you're a plastics manufacturer, or if you're in some kind of, a metal fabrication industry, you can look and see the typical amount of energy used per ton of product or per something like that but typically, a building is not going to use near as much energy as a particular process. And you really, comparing yourself to a library is really kind of not fair, apples and oranges. But if you compare yourself to other foundries and you're a foundry, then you can get a good idea of what's really good and what's not.
Thanks, Michael. Next question. How would you recommend peak energy demand be managed in a plant setting? And how would you compare in terms of energy efficiency, capital costs versus life cycle costs?
Yeah, the energy demand is a cost driver. You've got most of the utilities that we work with have either 15 or 30-minute interval data, and if you have 15 minutes, that's 96 points every day times 30 days. That's a lot of data points, and whichever one of those is higher in the billing period, you pay for that demand. And I kind of liken it to a pipe. The electrical utility has to provide you with a pipe so that you can get the most gallons per minute that you need at any time. Even if that pipe's 90% empty 80% of the time, you still need that 4-foot diameter pipe at least one day of the month. And that's how demand works. At least one point during the month, you needed 15 megawatts of power. And it might just have been for 10 minutes, and you never got close to that again for the whole month. But for that one dot, you got to pay for that. So ways to manage that is to look at, if you shut down on Fridays and start up on Sundays, don't turn every single thing on in the same 15 minutes on Sunday evening when you start up. Spread it out. Think about energy spikes and energy. You don't start all 3 chillers in the same 15 minutes if you're starting up. Starting up and shutting down can affect your demand. And again, that one point you really, really pay for. Capital costs versus life cycle costs. We look at that as a cost comparison. And if, would you pay, like I said, it's kind of like the premium efficient motor. Would you pay $200 more right now for a motor that is going to be 0.5% more efficient for the next 10 years? Probably. And you can crunch those numbers, but would you buy a more efficient, a $10,000 more expensive 1,500 ton chiller it's only 0.6 kW per ton operating estimated cost versus 0.75 kW per ton? Probably, you'd have to crunch the numbers, but if you can afford or justify buying that more energy efficient capital piece of equipment, most of the time, at least what we see, most of the time you really see that they will pay for themselves, especially motors. Motors are almost a no-brainer. If you can convince purchasing, we don't need to buy the cheapest motor, we need to buy the most efficient motor. And when I say most efficient, the most efficient practical motor, there's all kinds of crazy stuff out there that you can pay through the nose for. But a good NEMA premium induction motor, you should always buy. You should never, try to go cheap on a motor because you'll pay for it with electricity over the life of that motor.
Great, Michael. We've got about 2 minutes left. I'm going to picking a question that's a little harder to interpret, but in some ways it gives us an opportunity to provide a summation. And the question reads, you mentioned that if you have already bought the energy, what you pay for, you might as well make it as efficient as possible in your system. But what if you use more energy than you bought? How do you deal with that kind of a situation? Or is that not possible?
That's a good question. But yeah, I mean, basically, it's kind of a zero-sum game if you think about it. If once you've bought it, you can use what you bought, but you can't use all of it. You're never going to be able to use all of it. But what you want to do is that little bar that peels off of losses, that's what you want to make sure you minimize. Now, there are cases, for example, if you're a wastewater treatment plant and you bring sewage in and make biogas and then take that biogas and generate electricity, or if you have a solar farm on your back 20 acres, you can actually have energy. But again, that's coming in to your site. There's no, so unless you have a natural gas well on your property or some kind of electrical generator on your property, you're paying for that electricity. If you have a system that's making electricity or some other source of energy for you, then you would have to account for that differently. But basically, in the energy picture, if you excluding all other special situations, whatever comes across your electric meter and your gas meter, you're going to consume that. You're going to consume all of it. But how much of it was consumed to add value versus to be lost up a heat stack or lost from a compressed air leak or lost due to an air filter being clogged and a motor running harder or an inefficient motor. That's what you really want to focus on, is minimizing those losses and making that arrow that peels off of your bought energy to be as small as possible. But you'll never get it zero, or you'll never get it to where you get more energy out than you paid for. Great. Not physically possible.
Great, Michael. Thanks so much. In conclusion, I'll just read the comment of one of our attendees. They said, Michael, really well done. thanks for placing so much effort into this. And I'd like to
Thank
echo
you.
those remarks. You're very welcome.
My pleasure.
That's all the questions we have time for today. I want to thank Michael for participating in today's event. I'd like to thank our listeners for attending. We hope it suited your purposes. For more information, go to the website links noted in the interface. I'd like to, now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it as we use this information to improve our webcast. On behalf of CFE Media and Technology, we'll see you next time.